Hi, and thanks so much for click on this video and welcome to Integral of Symmetry. Integral of Symmetry is a new method in order to calculate any primitive of any function in any dimensional space. And in this seventh video, we are going to demonstrate, based on the fundamental of this new approach, integral of symmetry, why doesn't set the primitive of the exponential function raised to the square argument. We are talking about the following primitive in two-dimensional space of the classical calculus. Integral of e to s squared ds. It doesn't set. In order to demonstrate it, we are going to start what we left taught in the last video. In the last video, we could see that the primitive of the exponential function to the square argument, yet in circular expansion, e to s squared plus y squared, d circular expansion sy, e that exists and is pi times e to s squared plus y squared. And we used this result to calculate the volume under the surface of Gauss belt. This is z equal e to minus s squared plus y squared. And we calculated that primitive in that last video, and we find that this primitive using this result is integral of s to e minus s squared plus y squared, d circular expansion sy is minus pi to times e to minus s squared plus y squared. And to calculate that volume, we put the limit of the integration from the little circle, the smallest circle center in the origin, and extend to a greatest and greatest circle until the infinite to compass the sy plane. That is from s squared plus y squared equals 0, the smallest circle, to the infinite circle, which is s squared plus y squared equal infinite. And we put that limit of integration in that primitive s squared plus y squared equals 0 to s squared plus y squared equal infinite. And we plug in that limit in the primitive, and we have minus pi times open bracket e to minus infinite minus e to minus 0. And we have that e to minus infinite is 0. Pi minus pi times to 0 minus e to minus 0 is 1, to minus 1. So we have minus pi times minus 1, and we have positive pi. And well, we know that primitive allows us to calculate that volume. That was that we did in the last video. Now we add in this video, we add the following result. We know that this volume is the same. If we calculate that volume integral from s squared plus y squared to s squared plus y squared equals 0 to infinite of e minus s squared plus y squared. The circular expansion sy is equal pi, and this is equal is we use, instead of circular expansion, we can use a square expansion or rectangular expansion. There's no matter, it doesn't matter what is the shape of that figure in the plane xy. It no matter what shade it has, we can replace that shade for a square expansion, and the integral, the definite integral, is going to be the same. So we have from s equal minus infinite and y equal minus infinite to s equal positive infinite and y equal positive infinite of the same function e to minus s squared plus y squared. The square expansion or rectangular expansion, d is y, and this integral is the same in the multiple integral, is the same of that integral minus infinite to plus infinite of integral to minus infinite to plus infinite of e to minus s squared plus y squared ds dy. In the vocabulary of the multiple integral of the classical calculus. Now, this integral is the same. It's going to be the same, minus infinite to plus infinite of e minus s squared ds time integral of minus infinite to plus infinite of e minus y squared dy. And we can change the variable and put a common variable. We can say t, and we have integral, this is equal to integral minus infinite to plus infinite of e minus t squared dt time integral minus infinite to plus infinite of e minus t squared dt, and this is equal to integral of minus infinite to plus infinite of e minus t squared dt to s squared. And we know that this is pi. This is equal to pi. For that integral of minus infinite to plus infinite of e minus t squared dt is equal to a square root of pi. passing the power 2 as a square root. And what is the important here? What that matters here? The matter here is that this primitive is not exist. This integral, like a definite integral, exists and is fine. But as a definite integral, this integral, the primitive, is not exist. Exist like a definite integral from minus infinite to plus infinite, but not exist like a primitive. Why do I say that? Because this break the fundamental of integral of symmetry. The fundamental of integral of symmetry states that the argument of the function is going to be the same of the expansion. The expansion and the argument of the function must be consistent, must be matched. And in this case, they're not coincide because this is a circular expansion. This argument x squared plus y squared belongs to circular expansion and is being integrated by a square or rectangular expansion, and that not coincide, is not matched. For that, this primitive doesn't exist. For that expression as a primitive doesn't exist too. That expression also doesn't exist too as a primitive. Does not exist, and for that not exist, and for that that's primitive does not exist. And we have demonstrated that this primitive, this integral like primitive, is not, it doesn't exist. Then in the next video we're going to see another amazing result. We are going to solve to calculate our first differential equation in three-dimensional space. It will be nothing else and nothing less than the gravitational problem. And we are going to obtain, I assure you, you are going to obtain the general quadratic equation of the conic as a result of this differential equation, and without change of coordinate system to polar coordinate system. We are going to obtain the result of the general equation of the conic in rectangular system. For that, I hope to see you again in that video. Thank you.